Okay, so let's start with so we're going to talk about more about gradient flows. So let's start with the notion of a Riemannian gradient flow, and then we'll go to the Wasserstein one. So in my notation, Mg is a Riemannian manifold. So Mg is a Riemannian manifold. And so as with the Riemannian manifold, I have a metric tensor. So what is this metric tensor? So in a local coordinate, this is just given by some PSD matrix. So I have a point P in this manifold. I have two vectors V and W in the tangent space of P. And then I can write the metric tensor. This is the inner product. This is the angle in the Riemannian manifold in the tangent space. And how is this angle defined? Well, in Euclidean coordinates, this is just VI, GI, J, WJ.
The sound is gone again.
Oh God, I really don't know how to figure this out. Okay, is it back now?
Yeah,
Yeah,
back
it's
now.
back.
You still hear the echo, by the way.
I
A
don't.
little bit. It's not that bad. Just it's very slight.
I don't know how to get rid of this echo.
It's fine, I think.
All right, okay. Okay, so I have this in Euclidean coordinates. If I write down, I have a coordinate chart, then I have a matrix Gij. This depends on P. So Gij, this is a matrix, but that depends on P. And so now I can write my inner product VW as the double sum of VI, Gij, WJ. Now, if I have a function U that is smooth, so this is a function from the manifold to the real line, which is smooth, then for how I want to define what is the derivative, what is the gradient of this function U in this manifold. So that's my goal here. So there is a very natural way that you can talk about first directional derivative. So how do I define a directional derivative? So imagine this is my manifold. I have my point P, and then I draw a curve which is passing through P with a tangent given by V. So I take a smooth curve, any smooth curve, such that at time zero, this time is of course arbitrary. Zero could be one or half, it doesn't really matter. What is important is that at time zero, at some time it's P, and at exact same time, its velocity is V, where V is some vector in the tangent space. And now I can define what is the directional derivative by looking into how this function is changing as a function of t. So this is my u of rho t as a function of t. So this is a function of a real number. And just like in calculus, in real valued calculus, I can take a derivative d dt, evaluate this at t is equal to 0. And this will turn out to be like a dot product between some vector d of up and some vector, the velocity vector v at time 0. This vector d of up, which is this vector, this is what I'm going to call a directional derivative. How do I see this, that this is going to be some vector like this? Well, this is like, what is called Rie's representation theorem. For every velocity v, you can define this function. This is d dt of u of rho t. And then you have to argue that this is a linear function on the space of these velocities. And the space of velocity is the tangent space. It's a Hilbert space. And these linear continuous functions, they're given by inner products. And so this inner product will be given by another vector in the tangent space. And that tangent space is what I'm going to call my directional derivative. The Riemannian gradient, however, is something different. So the Riemannian gradient is given by sort of an inverse operation. We say that the Riemannian gradient of u in this manifold evaluated at P, this is an element in the tangent space P, which is given by the formula where you change this Euclidean dot to this Riemannian inner product. So at the velocity vector v, the Riemannian inner product with respect to this Riemannian gradient of u of p this is a Riemannian inner product, is given by this Euclidean dot product with respect to this initial velocity v. So any vector in the tangent space that satisfies this equality for all v is going to be my Riemannian gradient. Again, how do I know such a vector will exist? Again, Rie's representation. Okay. Now, why do we care about the Riemannian gradient and not about the directional derivative? It's because Riemannian gradient is an invariant under the change of coordinate systems. So, for example, I wrote down this G matrix, which depends on a choice of coordinate chart that we use. If I use a different coordinate chart, this representation of this metric tensor will be different. So this is an example of something. The metric tensor is something should be, what should I say, is intrinsic to the manifold, but its representation is different. So V on the left-hand side, this quantity, the inner product, the Riemannian inner product, this is an invariant, which means no matter what coordinate chart I use to write down my V and W, the left-hand side will not change. But each of these coordinate representations, they will all change. Vi, Wj, Gij, they will all change. But the transformation will be such that all the individual representations will change. When I look into this total sum, it won't change. Okay, so the left-hand side is a geometric invariant, it's an intrinsic object. The right-hand side is an intrinsic object, but each individual thing is actually depends on the coordinate chart. And because coordinate chart is somewhat of an arbitrary object, what you're really interested in is intrinsic geometry of the manifold. You want things to be intrinsically defined. So the same thing here, the directional derivative actually depends on the coordinate chart, and you don't want that. You can actually prove that the Riemannian gradient is intrinsic, so it doesn't depend on the coordinate chart. If you switch the coordinate charts, you still get the same Riemannian gradient. Make sense? All right, okay.
I have a que-
Yeah, sorry, go ahead.
I have a question about the fourth bullet. So the on the right hand side of the equal, you have a rho t. Should that be like gamma t, or it, what is rho t?
Oh, yes, this is gamma t. Thank you. Thank you, thank you, thank you. Yeah, this is
Okay.
gamma. Yes, yes. So you find the time derivative on gamma t at time t equals to 0. Any other questions? All right, okay. There's also a recap autocalculus. So our goal is to think of the set of all probability distributions on Rd with finite second moment as a Riemannian manifold. The metric on this Riemannian manifold is given by the Lecture-2 metric. This is the one that is coming from my optimal transport problem. How do I draw smooth curves in this Riemannian manifold? They are solutions of continuity equations. So these are curves. These are curves of probability measures that satisfies del t rho t plus the divergence of vt rho t is equal to 0, where what I'm given is rho 0, the initial point of the curve, and this velocity fields at every time vt. So these are my smooth curves. This PDE, you can think of it as a strong PDE in the sense that rho t of x as densities, which actually have derivatives with respect to t and derivatives with respect to x. This is too strong. What I really want is some kind of weak derivatives to exist so that if I integrate test functions, I can smoothly derive everything. So another way of writing this is that if I have a function which is cc infinity, then the time derivative ddt of integral of psi d rho t would be equal to the integral of gradient of psi dot vt rho t. Okay, so d rho t. So that would be the weak sense of making sense of this continuity equation. Now, these tangent velocities, they lie in L2 of rho t. So at every time t, the tangent velocity is lying at L2 of rho t. But they are not unique. But given a family of rho t that satisfies continuity equations, there are infinitely many choices of tangent velocities. But there is one choice that is unique. And that one choice is what we call the tangent velocity. Otherwise, they're just called velocities, not tangent velocities. And the tangent velocities actually lie in the tangent space. So at every probability measure rho, what is the tangent space at rho? You should think of this as essentially the subspace of L2 of rho, which is generated by gradients. So this is the closure in L2 of rho of the gradients of G, where G is smooth and compactly supported functions. So you look into all the smooth compactly supported functions, they're of course in L2, and you look into their closure, everything that you can obtain by L2 limits of such functions, and that's your tangent space. And so your velocities becomes unique if they are tangent velocities. Otherwise, there can be many other choices. Now, the metric tensor in this Wasserstein space, just like in the case of the Riemannian manifold, it is given by an inner product. Now we are dealing with functions. So V is some RD valued function, W is some RD valued function. Now at rho, the metric tensor, this is how I measured the angle, is given by you look into the dot product of Vx dot Wx and then you integrate with respect to rho x. Or in other words, this is nothing but the L2 inner product of V and W. L2 inner product at L2 at rho. Okay, so that's my metric tensor. Then we talked, Youngman has already talked about the concept of Wasserstein gradient. I'll give a slightly different perspective. So the idea is still the same, that I have a function from the space of probability measures to the real line, and I will include infinity. I need to include infinity when I'm doing infinite dimensional analysis because functions will typically not be defined over all probability measures, just some subset. So this is proper and lower semi-continuous. So proper means that it cannot be infinity everywhere. And lower semi-continuous means that, with respect to the weak convergence, topology of weak convergence is lower semi-continuous. So I have a function u, which is proper lower semi-continuous function. I want to define the gradient of this u on this infinite dimensional formal Riemannian manifold. How will I do this? Again, I will first define directional derivatives, and then I will switch my dot product to my Riemannian inner product. So how do I define this? So I have to define directional derivatives. So the way to define directional derivative is that I have to define smooth curves passing through a point rho. So what is a point? This is a probability measure. So it's a probability measure rho, and I have to take a curve that is passing through. So what are smooth curves? They are solutions of continuity equations. Now notice here I'm not writing down the full continuity equations, del t rho t plus divergence of vt rho t is equal to 0, because I don't need to. What I'm really interested in is a direction at rho along which my curve is moving. And that is simply given by v. So v is some element in the tangent space of rho. And I'm just looking into an infinitesimal part of this continuity equation where I say rho dot is negative divergence of v times rho. Okay, so this v is the direction along which it's moving. You may remember that the way to think about this is that there is a particle system at times let's say t equals to 0, and this particle system or this cloud of particles is approximately rho, and every particle has a certain velocity field along which they are moving. And then you measure what happens to the cloud of the particles at time t plus dt. And then whatever it is, that's my rho t plus dt. Okay. So this velocity field, the tangent velocity field v, is telling me the tangent. So it's telling me how my curve of probability measure is evolving with time. And so I just need to know what is it at time t equals to 0. And that's why I'm writing in the short form, rho dot is minus divergence v times rho. And now I apply my function u along this continuity equation u of rho t, and I will take the derivative at time t equals to 0. Just like in the Riemannian manifold case, I would get that there will be some function delta of u rho at x such that this derivative will be given by this inner product delta of u rho of x rho dot of x dx. How do I know such a delta of u rho of x will exist? Actually, it's the same argument. It is the same Rees representation argument. The previous Rees representation argument we were using was using it for the Hilbert space, which is the tangent space at a point P in the Riemannian manifold. Over here, that same argument applied to L2 of the Lebesgue measure will tell you that this will exist. Okay, so there will exist some function such that if I take my directional derivative of u of rho t along each one of these velocity vectors, tangent vectors, I would get that this would be equal to rho dot of x dx. And now this rho dot of x, this term is over here, is the right-hand side of negative divergence of v rho. And so if I do an integration by parts, I get that this is negative del rho u of rho of x, divergence of v rho dx. And now I do an integration by parts, this divergence becomes a gradient, the negative sign vanishes, and I get this. This is the gradient of the gradient of the first variation, the L2 first variation of u. This is a vector in d dimension. This is the Euclidean dot product with the velocity field, which is another vector in the d dimension. And now everything is being integrated with respect to rho dx. But you realize that this is actually the L2 inner product of one vector field, u rho, and the other vector field v in L2 of rho. And therefore, I have basically written this down exactly as I did it for the Riemannian manifold. I found out a vector field which is the gradient of the first variation of u of rho, such that the metric tensor with every tangent velocity v is given by this directional derivative. And therefore, this object must be my Wasserstein gradient. Are you following this analogy? How do I know this Wasserstein gradient again exists and belongs to the tangent space? Same, Rees representation. If it doesn't belong to the tangent space, just project it down to the tangent space. Okay, so this is the formal analogy with the Riemannian calculus, which tells you how to define what is the Wasserstein gradient of this function. So I'll write down the first definition. Again, Young must have mentioned this. I'm part of this class is just putting them in my notations. That's it. So what is the Wasserstein gradient? I'll give several definitions. It's the first one, which is, I would say, the most explicit one, and I'll come to some of the other ones. So if I have a function which is proper lower semi-continuous function u, which is at rho is in the domain of this function, assuming everything below is well defined, you should define the Wasserstein gradient as the gradient of the first variation of u at rho. Now this is a function, this is a form of a gradient. Therefore, this is in the tangent space. You have to guarantee that this is actually L2 square integrable to be actually in the tangent space, but I am assuming everything is well defined. Okay. The point of this definition is that no matter what other definition you use, it will match with these definitions. If you have an explicit function and you have to make a write down a guess of what is the Wasserstein gradient, this is the definition you should use. You should formally calculate the first variation of the function and take a gradient. So let's see an example. Everybody's doing okay? All right, so let's see an example. So my function is very simple. It's my potential energy function. So I have a function v, and I'm looking into u of rho. This is a function of my probability measure rho. This is a function u of rho, which is nothing but the integral of vx rho dx. Very simple function. Let's see what happens if I take directional derivatives. So I take a curve passing through rho. So rho dot is minus divergence of v rho. So v is my tangent velocity. I take this function and I evaluate it over my curve rho t. So this is my function Vx rho t dx. Now I take the time derivative del t. If I switch my derivative, time derivative with respect to the integral, this derivative now acts on rho t, and that gives me rho dot at time t equals to 0. And so this becomes minus Vx divergence of v rho dx. And as before, I do an integration by parts. I get gradient of v dot Vx, the velocity vector, times rho dx. And so what do I learn from this? That no matter what v is, this is the equation that I get. And so the first variation is simply given by the function v that you're integrating. And the Wasserstein gradient is given by the gradient of v. It's cool. So if I take Vx to be 1/2 norm x squared, then what is the gradient of Vx? That's just x. So if I'm integrating u of rho with 1/2 of norm x squared, then I'm looking into some squared error moment, the second moment, and the directional derivative is just this function, which is scalar, and the Wasserstein gradient is the vector, which is the gradient of this scalar.
I have a question. How
Yes.
should I think about time dependence with the velocity? Will I need to have different velocity fields and at any one point there's a different rho and a different velocity that's sort of instantaneous at that one time point? Or are we studying what happens when there's like a fixed velocity field?
No, so if you think about Euclidean gradient, forget about manifolds, take a Euclidean space. You have a function f and you're looking into what is Euclidean f or gradient of f. So it tells you, well, use your calculus formula will tell you, well, gradient of f is like partial derivatives. You take the partial with respect to a first coordinate, partial with respect to a second coordinate, and so on, right? This is a usual formula. But what are those partial derivatives actually representing? It's representing curves passing through the point where only the first coordinate is changing and nothing else is changing. Then the second one, second partial is only the second coordinate is changing, nothing else is changing. So you're drawing these curves parallel to the Euclidean axis, which are passing through those points, that point. And then you're computing directional derivatives of the function along those. And those are what are giving you each one of your coordinates in the gradient. Now, there's nothing particularly special about the axis direction. You could do it along any direction, and that gives you all the directional derivatives. But you need a sufficient number of them to figure out what they to entire gradient vector. Does this make sense? You're basically thinking of the gradient as how it is acting on these tangent vectors.
Yeah, I feel like I keep asking the same question about is all of this an instantaneous relationship at a certain point where we're infinitesimally morphing rho to a nearby rho t plus del t,
Yes,
and that at that specific infinitesimal point we have a small, velocity field v. Because
yes.
I'm thinking about the whole flow, the whole curve, which can surely the velocity field has to be different to move particles in a different way at those different time points.
Exactly. So this is all instantaneous. Any gradient is a local object, right? You
Yeah,
calculate gradients. It only depends on an infinitesimal neighborhood around this point. So
yeah,
this gradient is also that.
okay,
It is very local. So as you move along the curve, your gradients are going to change.
yeah, good,
This example doesn't show it because it always gives the same gradient as you move along the curve, but the next one will.
okay.
Okay. Any other questions? All right, okay. Here's another example. Now, in this case, my function is my entropy function. So U of rho, this is entropy of rho. Now, if you remember, this entropy function is not defined everywhere. It's only defined when rho is absolutely continuous, so that rho has density. If it does have density, then it is given by the integral of rho x log rho x dx. So it's absolutely continuous function. Now, I want to define its Wasserstein gradient. How will I define its Wasserstein gradient? Well, first I want to compute its directional derivative. So take take v, which is in the tangent space of rho, and you infinitesimally change your rho by this velocity v. So again, I have a bunch of particles whose shape is like rho, and each one of them moving slightly by a velocity v to make it a different rho, different tangent velocity, sorry, different configuration. So, and now then I apply my entropy function along that curve, and I take a time derivative. So I have rho tx log rho tx dx. This is my entropy function, entropy of rho t. And I take a time derivative at 0. Now, when I take this derivative inside this integral, I can apply my multiplication rule. So in the first step, I would get rho dot. So because this is time derivative at rho t, that gives rho derivative at 0. So that's rho dot. The other one remains the same, log rho, the time t equals to 0. And for the second part, look at what is happening here. When I take the time derivative, del t of log of rho t, so what do I get? I get del t of log of rho t, everything evaluated at t equals to 0. I get this is equal to del t of rho t divided by rho t, right, by chain rule, evaluated at t equals to 0. And that gives me rho dot over rho. And so this rho then cancels with this rho, and all I'm left with is rho dot. Good. This is simple. Just do multiplication rule. Now I claim that this integral is 0. Can anyone tell me why? Why is for any curve of probability measure, the integral of the time derivative of rho must be 0.
Yeah,
Why?
I think you can take the time derivative outside the integral. It integrates to a constant, and then you just not
Precisely.
changing.
Yeah. If you pull out the derivative outside the integral, then I'm taking a derivative of the total integral of a set of a family of probability measures, and that's always 1. And so a time derivative is 0. So this term just drops out. This is always true. And so then only thing that I'm left with is this guy, which is the integral of rho dot log rho x dx. And now I plug in that rho dot is equal to minus divergence v rho. And now I do my integration by parts. So minus drops out and the gradient sits over here, and I get gradient of log rho x vx rho x dx. And that gives me my formula. Now you'll notice that I'm doing some things which require smoothness. All this is like, I'm doing integration by parts, I'm taking derivatives, I require smoothness. First thing that you should notice here that I'm taking my velocity field in the set of tangent velocities. Over there, it is generated by the gradients of smooth compactly supported functions, and those are just fine. And for the rest of it, you have to guarantee that this log rho x actually has a gradient, and everything is nice, and they have to be externally guaranteed. Okay. But if everything works out fine, then I'm getting that my time derivative of the integral of rho tx log rho t of x, which is my entropy, is given by my L2 inner product of this quantity, which is gradient of log rho, and my velocity vector v. This tells me that my Wasserstein gradient is the gradient of log rho, which is sometimes called the score function. And if you just follow the argument, you see that the L2 first variation is just given by log rho. So as before, my first variation is a scalar function, and my Wasserstein gradient is a vector function, because Wasserstein gradient lies in the tangent space, and it's telling the velocity fields of particles underlying. Going back to Jeffrey's question, this is an example where the Wasserstein gradient is actually changing with rho, because it's the gradient of log rho. So as you change rho, the gradient of log rho is changing. Good. Any question about this example? All right, okay. So here's a general formula, which is what you can use to always compute these Wasserstein gradients. So suppose your function is given of this type, that u of rho is the integral of a function f applied to three arguments. So x, this is a vector in Rd. Rho x, this is an element in R because this is the density at x. And the gradient of the density, gradient of rho x, so this is again in RD. And then you integrate this, and this is only for absolutely continuous functions, absolutely continuous densities. Now, if you have a function of this type, then there's a very neat formula to calculate the Wasserstein gradient. Its L2 first variation is given by the following. Notice the second coordinate. This is scalar. So F2 represents the gradient with respect to the second coordinate. Okay, so this is the derivative with respect to the second coordinate, that's F2, applied at x rho x gradient of rho x. So it's a scalar. Now F3 dot, this should be, the 3 should be here actually. This is the divergence calculated with respect to the third argument. Okay, this third argument is vector valued. So there's a divergence that is associated with it. So you calculate the divergence with respect to the third, partial divergence with respect to the third argument while keeping both the first and second arguments the same. And this is again a scalar. That's your first variation. So what is the Wasserstein gradient? This is the gradient of the first variation. So it's the gradient of all this entire quantity on the right-hand side. All right. For a particular example, when I'm looking into my entropy function, so when u of rho is integral of rho x log rho x dx. So you can see here that there is no dependence on the function x. There is only dependence on the middle portion, which is my rho x log rho x, and there is nothing in the third argument. There's the gradient of rho x doesn't appear here. So this part is 0. The second component is 0 because there is no divergence there. And for the first one, I just take derivative of the function. So I have a function which is fx equals to x log x. I shouldn't use x here. Let me change the notation. So fu is equal to u log u. So that's my function of my rho x. And so if I take derivative with respect to u, I get f prime of u. So my first term gives me, so log u, and the second term gives me 1. Okay, so the 1 really doesn't play a role here. It's just log u is my first variation. And so my Wasserstein gradient is the gradient of f prime of u. So this is my gradient of log u. So gradient of log rho x. Is this calculation clear? So this general formula is what you will actually use in practice to calculate this Wasserstein gradient. You write it as an integral of a function of x, the position, the density, and the gradient of the density. Calculate its first variation using this formula, and then take the gradient, and that's your Wasserstein gradient. You can find this formula in let's say, in Ambrosio Gili Safari or any of the other textbooks too. Any questions? You understand this formula now. Let's see another example. Okay, before we get to another example, which is Kullback-Leibler, I want to connect it back to geodesic convexity. Younghoon has already discussed this, but I just want to go over again in my own way. So what happens when I have a function that is lambda geodesically convex? So what's a function that is lambda geodesically convex? We have talked about this before. So our function u is lambda geodesically convex. If we have talked about geodesic convexity, and this is a generalization of lambda geodesic convexity, Younghoon had mentioned it. If along every constant speed geodesic, if rho t is a constant speed geodesic, then if you apply this function u of rho t, then this function t going to u of rho t satisfies the following property. That u of rho t is less than or equal to 1 minus t u of rho naught plus t u of rho 1. That's just convexity. Minus lambda over 2 t times 1 minus t w2 square rho naught to rho 1. Okay. This is an analog of a Euclidean definition. So I say my function f from Rd to R and infinity, this is lambda convex, if fx minus lambda over 2 norm x squared is convex. So what does that mean? It means that the function f is more convex than the function lambda over 2 norm x squared. What is the function lambda over 2 norm x squared? That's just a parabola. It's a parabola which is growing at the rate of lambda over 2. And the function is lying above. It's more convex than that. It has at least this much convexity. So the other way to think about it is that if everything is smooth, then you can take the Hessian of f, and the Hessian of f is going to have a lower bound, which is lambda times identity. So all the eigenvalues of the Hessian are going to be at least lambda. Now, if lambda is positive, this is the same thing as saying uniformly convex. Lambda uniformly convex, right? All the eigenvalues are bounded below by lambda. But if lambda is negative, then something interesting happens. If lambda is negative, then the function f need not be even convex. I allow for concavity as long as that concavity is bounded below. It cannot be too concave, right? So this entire theory of gradient flow is based on this notion of lambda convexity, a lambda geodesic convexity. But you should not think that you can only deal with convex functions. You can also deal with functions which are semi-convex, which means that it might be concave, but there is a lower bound on how bad it can be. Arbitrary concave functions cannot be allowed. Okay. Now, for the case of
I have a
convex,
quick question.
yes, go.
If you go back to the previous slide, can we put the Euclidean analog in this same exact, I'm assuming we can, but can we put the Euclidean analog in this same exact kind of form?
What is
The synthetic form, I suppose, like
the
for
Hessian?
I guess like when you write f of x minus lambda over 2 norm of x squared, could we also write that in kind of a similar form as the above expression?
Hmm, okay. Yes and no. The problem over here is that I mean, here, look at how this is being done. I'm defining this as a function of W2 squared. So I'm looking into W2 squared rho naught rho 1, right? So how should I say this? I need to have the endpoints to introduce this W2 squared distance. The Euclidean norm square by itself doesn't really mean much in the Wasserstein space. It's just a second moment. So I have to write down something in terms of the W2 squared distance. You can, if the function actually has a Riemannian Hessian, and that actually many functions do have a Riemannian Hessian, we'll not talk about it, but there's Riemannian gradient, but there's also Riemannian Hessian. If it does have an Hessian, then yes, you can say that the Riemannian Hessian is a lower bound, and that can actually be justified.
I guess what I'm asking is like if we take the Euclidean analog and restrict to just lines in RD, like
Yes,
parameterized lines in RD, then we would get
you would get this
the
one, exactly. You would get this one,
yeah.
correct. This is the more
Okay.
robust definition.
Okay. Thank
Correct.
you.
Every notion of convexity should be essentially you should be able to define it by drawing one-dimensional lines, right? Any useful notions of convexity. Yeah. Any other questions? All right, now what do we know about gradients of Euclidean convex functions? We know that if you have in the Euclidean space, if I have a convex function, it is given by the following property, that this is a convex function if and only if I can draw the tangent, then the curve will lie entirely above the tangent. And this is also true if the function is not differentiable. So if I look into this function, which is like something like an absolute value of x, then this is a tangent, and so is this. But this is not a tangent. I can't just like draw through the curve. That's not allowed. So there is a very geometric way of describing what a gradient or what is a subdifferential of a convex function in Euclidean space, which is to say that if I have a function f, then anything is a subdifferential. So I'm looking into, let's say, this point x, and this velocity v if f of y is greater than or equal to f of x plus v dot um, y minus x. So then v is in the subdifferential of f at x. Right? This is a definition that we know and love. It makes sense. Convex functions means that you draw a tangent and the function lies above the tangent. So can I write such a definition for the Wasserstein space? The answer is yes. You can analogously define the following definition of what is a subdifferential of a function. This doesn't require smoothness. Subdifferentials can be defined much more generally. So we say that if I have a lambda convex function, take a vector field psi, which is in the tangent space of rho. You see that this is a subdifferential of the function u at rho. If for all other probability measures mu, your function u evaluated at mu must lie above u of rho. This is my first order approximation, and this is my second order lower bound. Where is the second order lower bound coming from? Well, if I also assume that Hessian of f is actually bounded above by lambda times identity, then my second order Taylor approximation will give me that this is bounded by lambda over 2 y minus x norm squared. And so this would inspire this following definition. Right? If I do my second order Taylor approximation, I will get the Hessian of f. The Hessian of f is bounded by lambda times identity. The identity will give you norm of y minus x squared, and the Hessian will just give you this bound by lambda. And so for the Euclidean case, if I have a lambda convex function, then that's the bound you would get. You can see that not only that the function is above the tangent, but you can also quantify how much above the tangent it is, that you would be able to fit a sphere touching, you'd be able to fit this sphere touching this point, or rather a parabola touching this point, which is growing at the order of lambda, rate lambda. They would lie inside. Okay. So similarly, for the Wasserstein space, I can do the following definition. I can say my function u admits a subdifferential, and the function u is lambda convex. It admits a subdifferential. If for every other mu, u of mu is greater than or equal to u of rho, this is my inner product, psi dot t minus identity L2 of rho plus lambda over 2w2 squared. So what is t minus identity? This is the Brunier map transporting rho to mu. I had explained this idea before that y minus x in Euclidean, when you do your Wasserstein calculus, y minus x is the vector connecting x to y. When you're doing your Wasserstein calculus, this vector becomes the Brunier map minus identity, okay, or the negative of the Kantorovich potential, the gradient of the Kantorovich potential. And so you take this L2 inner product, replacing the Euclidean dot product, and this lambda over 2, the Euclidean norm square, becomes lambda over 2 W2 square distance between mu and rho. And that becomes a perfectly good definition. Now, does this definition match with the previous definition? There's a result in Ambrosio-Gilli-Safari which says that if the density is C1, then the previous definitions match. So the definition that we wrote down, which is the gradient of the first variation and everything is well defined, will also satisfy this above tangent representation whenever you're working with a density which is C1. And the function u is lambda convex.
Sorry, just to clarify what you just said, you said the previous definition is in the definition of the gradient of u?
No, this is
Okay,
my
okay.
previous definition. My previous definition is that if u is of this form, then the Wasserstein gradient is the gradient of the first variation of u.
Okay,
Now I'm
thank you.
saying that if u is in addition lambda convex, then this definition also gives me the following property that it lies above the curve, lies above this tangent.
Okay, thank you.
A final definition of Wasserstein gradient is very, very useful, although it may not look so, but it's actually very useful. This is the variational representation of the gradient. Now, Wasserstein gradients are tricky business. As you can see from here, everything has to be nice and smooth to make sense of things, to be able to define things. Now, analysts don't like those things because they would like to define things in a more robust way, which doesn't really depend on whether you can take derivatives. And one of these robust ways of doing this is by using optimization. And this is the variational representation where you are going to write down where we are going to write down the Wasserstein gradient in its variational form. So let's see what this is saying. This is quite new, and so pay attention to this. But this is critical. So the variational representation goes like this. So suppose I have a lambda convex function u on the probability measures, and tau is some positive number. Now, rho is some element in the Wasserstein space, but rho doesn't have to be absolutely continuous. It can be just any rho. Now consider the following object. You are minimizing u of mu plus 1 over 2 tau, the Wasserstein 2 squared distance from mu to rho. This minimization is happening over all P2 of RT. And you call this minimum, the argument, to be rho tau. Now, what is this actually doing? I'll come to the later, but let's see what it's actually doing. Now notice this the first term here. You should think of it as a penalizer. So if the first term, if tau is infinity, then the first term just drops out, and I'm simply looking into the minimum value of u. Now if tau is not infinity, in fact we would like to be tau to be very close to 0, then what is this first term actually doing? It is saying that essentially you should only look into a W2 ball around my rho of a radius which is about square root of tau. So my rho is here. I would look into a ball which is of W2 ball such that the W2 distance from, so W2 square distance from rho is of the order of tau. And I can discard everything outside of it. Because if I take something which is much bigger than tau, then I would divide this by this tau, 1 over 2 tau, and tau is very close to 0. This term will become very large. And so whatever is in this set is not going to be in your argument. Right? So you're essentially looking at a very tiny ball of radius square root of tau in the Wasserstein space sense around rho. And now I'm taking the minimum. Is this clear? So as tau goes to 0, I'm taking a minimum over a smaller and smaller and smaller radius ball around rho. And you'd expect that this rho tau will actually converge to rho, and it does. So rho tau will converge to rho as tau goes down to 0. Okay, so that's my definition of rho tau. So this result of Otto is very useful. In general, if your function is rough or rho does not have densities, you can't quite define what is the Wasserstein gradient of u at rho. But you can always define what is the Wasserstein gradient of u at rho tau. And now as you take tau going to 0, you're getting a sequence of Wasserstein gradients which is converging to that rho. Whether or not that's the Wasserstein gradient of rho is something else, but at least it gives you some approximation of Wasserstein gradients. So this is a theorem of Otto. Let T of tau be the Brunnier map which is connecting rho tau to rho. So here is my rho tau somewhere here. And then rho tau to rho is what I'm connecting. That's my T of tau. Now look into the map, which is T of tau minus the identity map divided by tau. It's like something like a derivative. This is a subdifferential of u at rho tau. So what did we learn from this? We learned that u always admits a subdifferential at rho tau. That's one. You can always find this subdifferential by looking into t tau minus identity of tau. And as tau goes to 0, this rho tau is converging to rho. And so you're kind of approximating the gradient at rho, whether or not it exists, by proper gradients at a sequence of points that is approaching rho. Okay. You can show, and this is done in Ambrosio Gilles Savare, that if u actually admits its own subdifferential, then it also matches with this definition. Everything is, they're all consistent. But this is a very robust definition of Wasserstein gradients at nice probability measures, which are close to rho. Right? This is something interesting to think about. Like if you have a probability measure rho, let's say it's empirical distribution. This is obviously purely atomic, and you don't expect, let's say, entropy to have a gradient at your empirical distribution. If I ask you, is there a way that you can smooth out your entropy so that you can smooth out your empirical distribution so that your entropy is well defined, you'll come up with multiple ways. There is kernel smoothing. There are lots of ways that you can take a purely empirical distribution and you can smooth things out such that you get entropy well defined or the gradient of entropy well defined. This is one such way. And it comes with its natural, there is some monotonicity and nice properties of this way. This one such way is a bit unintuitive because it's not something like, okay, you just add Gaussian noise to it and make it smooth. What it is saying is that you solve a variational problem and you look into the minimizers of that variational problem. And that minimizer is always going to have admit a Wasserstein subdifferential. And that subdifferential is simply given by t tau minus identity over tau. Okay. Where did you get this idea from? Where did this very unintuitive idea of gradient come from? It again comes from Euclidean cases. So let's see what is the Euclidean nature of this object. Everybody fine with this? Okay, so let's see the Euclidean definition. So if you have a function in the Euclidean space, let's say the function f, which takes Rd to R times R and infinity, then in this Euclidean space, fix a point x and a step size tau positive. Now you consider this object, which is the argument over y, 1 over 2 tau y minus x norm square plus f of y. If you've done some optimization in machine learning, this is a very natural object to look at. People do this all the time. Okay, so again, same idea. I'm looking into the minimum of f around a Euclidean ball of a radius of square root of tau, of order of square root of tau. Anything bigger, that won't be in the argument. And now as tau goes to 0, x tau will converge to x as tau goes down to 0. Now, if I do a first order condition on this optimization, so what is x tau? Well, what we would notice from here is that the gradient applied to this thing here, if I evaluate at x tau, I would get 0. Right, that's my first order condition. So what happens if I take the gradient? If I take the gradient here with respect to y, the first term gives you y minus x over tau, and that's here. X tau minus x over tau. The second term gives you gradient of f at y. So if I shift it there, I get negative gradient of f of x tau. Good. So what this tells you is that your gradient of the function at this point x tau is given by join the point x tau with x. So look at the vector that is joining x tau to x, so x tau minus x, and you divide by tau. Or if you switch the minus sign on that side, you get gradient of x tau is x minus x tau over tau. Right? And so that's the thing that we do here. I'm joining my x tau, x minus x tau. This is my t of tau minus identity over tau. And that's my subdifferential of u at rho tau. Okay. And so it's coming from this Euclidean analogy again. Good. So we learned three definitions for this Wasserstein gradient. The first one is purely formula. The first definition is just telling me if I have a function, how should you actually calculate this derivative? And that's this formula. If you have a function formula, which is an integral of f of x and rho x and gradient of rho x, it should be given by, well, this is my first variation, this is my gradient. When you compute this formula, you have to keep in mind that not everything is going to be well defined. Some things only are well defined as long as things are smooth, otherwise they're not well defined. So how can you actually define it for other points? That's where the other two come into this point. You can show that if U is lambda geodesically convex, then this is a definition that you can use, which is this, the curve lies above the tangent. And then you can show that, okay, this formula that you computed will give you a subdifferential. And the third one is that, okay, the function may not have a nice derivative at the point rho, but you do a tiny radius ball around that point rho, and you look at where the function is minimized in the tiny radius ball. That argument, that point is actually much nicer. And there you can define things and you can define the gradient. And then you can take tau going to 0 so that you have some kind of approximation of the gradient of the function u at rho. And that's why this is useful. Okay, so sorry, any questions? All right, okay. Let me just explain a bit more how from going from Euclidean to this definition of given by Otto by doing actually autocalculus. So I have this problem that rho tau is the argument over all probability measures mu of 1 over 2 tau W2 square mu to rho plus u of mu, right? That's the argument that I'm trying to solve. Now, if I want to get exactly the same formula, which I have written in the Euclidean case, I can actually also do it now in the Wasserstein case. Why? Because I can have a first order condition of optimality in the Wasserstein space. All I have to guarantee is that the Wasserstein gradient must be zero. Right? So how do I get this? If I have a function u which is minimized at a point, then any directional derivative along that point must be zero by Euclidean logic. And therefore, the Wasserstein gradient must be zero. So a natural way to solve this problem is let's just take Wasserstein gradient on the right-hand side and put it equal to zero, and that gives me a characterization of what is rho tau. Now, the Wasserstein gradient, I have to take the Wasserstein gradient of this entire quantity. And so it's the Wasserstein gradient of the first term plus the Wasserstein gradient of the second term. The Wasserstein gradient of the second term is exactly what it is. This is by definition gradient of Wasserstein gradient of u of rho tau. Remember, rho tau is where the minimum is achieved. Now, the Wasserstein gradient of the first term is something that we have already computed before in my previous class. Okay, remember that this should be compared with the Euclidean 1 over 2 tau norm of y minus x squared. And if I take derivative with respect to x, I get exactly y minus x over tau. And then if I switch it to my Wasserstein gradient, I get this is 1 over tau identity minus t of tau, where t of tau is taking my rho tau to rho. This is my Kantorovich potential, the gradient of the Kantorovich potential. And so I can actually take my Wasserstein gradient of the right-hand side, put it equal to 0 by my first order condition, and that tells me this formula, if I rearrange, that this gradient, Wasserstein gradient of u of rho tau is t of tau minus identity over tau. Right? Okay. This step, the reason Otto discovered this step is because this is the first step of JKO. This is rather what I should call a JKO step. And we will come to this later. But this is very critical in doing Wasserstein gradient flows. This is that you define your every step of the gradient flow as a variational problem. This is the JKO step. Let's see another example. Kullback-Leibler. So take u mu to be a density which is of the type e to the power minus v. Now take v to be a semi-convex function or semi-convex function, which means e to the power minus v is log semi-concave. So remember that if v is convex, then I say that e to the power minus v is log concave, which means that if you take log of e to the power minus v, you get concave function. So if v is semi-convex, then e to the power minus v is log semi-concave. Okay, to take the log of e to the power log of mu, you get my semi-concave function. Now look into a Kullback-Leibler with respect to this mu. So u of rho is Kullback-Leibler of rho with respect to mu. So as usual, this is the entropy of rho plus the integral of Vx rho dx. We have already shown that this is has a Wasserstein gradient. We have already shown this has Wasserstein gradient. So in fact, I've assumed that V is log convex, so everything satisfies all three definitions. And so what is the Wasserstein gradient of the Kullback-Leibler? It's the Wasserstein gradient of the entropy, which is a score function, plus the Wasserstein gradient of the potential, which is the gradient of V. And if I combine these two, I get what is called the relative score. So this is a relative score function, which is looking into the log likelihood, the log likelihood of this rho over mu, and then it's taking its gradient. This is relative score. Now this element is going to be in the tangent space, and so you can ask what is its size? And its size is actually an important quantity, that the L2 norm square of the Wasserstein gradient, it's given by obviously by this formula. This is called a relative Fisher information. It's a relative Fisher information. It becomes a usual Fisher information if you take mu to be 1. Okay. So for Kullback-Leibler, I want you to remember that the Wasserstein gradient is a relative score, and the norm square of the Wasserstein gradient is relative Fisher information. Gradient flows. So Youngman has already.
That seems
Sorry, go ahead.
related to score-based variational inference.
Of course, it's related to score-based variational inference. It's also related to all these image generations. We're using diffusion models. Of course.
So this would be can we see the objective here that those usually optimize? Is it just this?
The objective function is Kullback-Leibler. And when you optimize Kullback-Leibler, you get these gradients and the norm square of the gradient coming up as relative score and relative Fisher information.
Okay, thank you.
But I'm going to bring my diffusions now. So gradient flows. So Youngman has already defined this, but let me again go over this again. So I have a function u, which is the set of all probability measures with finite second moment. I take some element rho naught. This is in the domain, and I'm going to define my Wasserstein gradient flow. So what is Wasserstein gradient flow? This is an absolutely continuous curve, which satisfies continuity equation, this guy. For the continuity equation, the velocity is very special. The velocity is the negative of the Wasserstein gradient of the function u applied to rho t. Very, very, very special formula. Okay, you should compare this with Euclidean gradient flows, which are smooth curves, which are solutions of the Cauchy problem. Time derivative xt is negative of gradient of f of xt. It's very similar. Okay, this is a well-defined object, intrinsically geometric, but its significance only comes from by looking into examples. So let's look into examples. So the first example, I'm going to take my function u of rho to be half entropy. Why half? Well, because I've explained this sometimes that in probability, this half is important. So you get half entropy of rho. And so what is the Wasserstein gradient of the entropy of rho? We know that this is the score function. So what is the Wasserstein gradient flow? The formula for the Wasserstein gradient flow is del T rho t plus the divergence of Vt rho t is equal to 0, where Vt is the negative, the Wasserstein gradient of u of rho t. And so I can also write it in the following form, that this is del T rho t is equal to divergence of the Wasserstein gradient of u of rho t times rho t. Okay, just change it to the other side. And if I do the same thing here, I get the Wasserstein gradient is a score function. So 1/2 of the score function is 1/2 entropy. And so if I gradient of log rho t, this gives me gradient of rho t over rho t. This rho t will cancel with that rho t. Divergence of gradient will give me Laplacian, and I get del t rho t is 1/2 the Laplacian. This is, of course, nothing but the well-known heat equation. So the solution of the heat equation is the Wasserstein gradient flow of entropy. But for probabilists, the definition that of the heat equation that makes more sense is that if I run my Brownian motion, starting with initial at rho naught, Okay, so I have my bt, this is my Brownian motion, where b0 is coming from rho naught. And then my law of bt at time t, this is rho t. So all these particles at time 0, they are following independent Brownian motions. And I'm measuring them again at time t, and I'm saying, what is their law? Well, that's rho t. That's the marginal flow of this Brownian motion. Rho t is the solution of the Wasserstein gradient flow of entropy. Now, the reason this is remarkable is think about what is the gradient flow trying to do? The gradient flow's objective is to minimize a certain function. In this case, the function is entropy. Where is the entropy minimized? Well, actually, it doesn't get minimized. Entropy becomes smaller and smaller as your density gets more and more flat, right? At Lebesgue measure, it becomes negative infinity. But you can think of it like its minimum is attained at Lebesgue measure, where things are just diffusing out. What are Brownian particles going to do? If you start a Brownian motion by its very nature will diffuse out. And at time t equals to infinity, you can think of it as if the Brownian density has become Lebesgue measure. So at time infinity, it does get to minimize this entropy. But a gradient flow, and we will see this more rigorously later with JQ, is not just minimizing a function. It is also saying that it is the most efficient way to minimize a function because you're following the direction of the negative of the gradient. And so what this is saying is that the Brownian particles themselves, in some sense, is decreasing entropy from time t to t plus dt in the most efficient way possible. Okay? This is something that will be made more rigorous by JKO, but this is an idea that you should keep in mind. That's my first example. My second example, I'm going to look into Kullback-Leibler. So my mu is equal to e to the power minus v. My function u of rho is again 1/2 Kullback-Leibler rho to mu. And so if I look into what is my Wasserstein gradient, I get this is my score function plus the gradient of v. If I write down what is my Wasserstein gradient flow, del t rho t is the divergence of the Wasserstein gradient flow time the Wasserstein gradient times rho t. I get this formula, and if I write this down, I get this is 1/2 Laplacian plus 1/2 divergence of gradient of v times rho t. This may seem strange, but this is nothing but the Fokker-Planck flow. This is the Fokker-Planck equation. How did we get the Fokker-Planck equation? Again, from our diffusion. The diffusion in question is what is called commonly the Langevin diffusion. This is a negative sign here. What is a Langevin diffusion? This is probably the most common diffusion that you can use to do sampling from a certain density. It's given by the following stochastic differential equation. dxt is minus 1/2 gradient of v of xt dt plus dvt. This is the stochastic differential equation. It has a certain invariant distribution, which is e to the power minus v. So the law of xt, which is rho t, converges to e to the power minus v. So if you are somebody who does statistics or somebody who does machine learning or generative modeling or something like this, if I tell you, okay, I need a sample from e to the power minus v, your first instinct will be to somehow simulate the Langevin equation in some discrete way. There are a number of discrete ways, but they're all trying to simulate the Langevin diffusion. This is the most common diffusion to get a sample from this invariant distribution e to the power minus v. If I look into the marginal flow of this Langevin diffusion, rho t, this satisfies this particular PDE, which is the Fokker-Planck equation. And now we have learned that it is also the gradient flow of Kullback-Leibler with respect to e to the power minus v. So what does that mean? Well, when is v of rho minimized? This is minimized, this is 0 exactly at rho is equal to mu, and otherwise it's strictly positive. So it's minimized at e to the power minus v, and your gradient flow is converging to its minimum. And so rho t is converging to e to the power minus v. You have to assume that v is semi-convex. So that much is fine. But it is saying something again about infinitesimal optimization, because a gradient flow is the fastest decay of a certain objective function. It is saying that anytime t to t plus dt, your Langevin equation, the particle system, is decreasing the Kullback-Leibler in the most efficient way of possible as long as you measure it in the Wasserstein-2 distance. Cool. I think I will stop here. So the next class, I will start with the rigorous JKO justification. But I want to stress here, so what we have introduced here are three concepts. One is that the abstract notion of gradient flow in the Wasserstein space. Two is that the corresponding continuity equations, which is these families of PDEs. And three are diffusions. These are diffusions whose marginal flows satisfies those PDEs. These three things, what I'm showing here, they are basically equivalent. So you want to understand the gradient flow, you can study either the PDE or you can study the diffusion. You want to understand how fast the diffusion converges, you can go back to the gradient flow and understand the geometry, or you can study the PDE. You want to understand how the PDE behaves along its path, you can either go with the gradient flow or you can go for the diffusions. The last two, the connection between PDE and the diffusions is well known for the last 30, 40 years and has been well utilized in many concepts. The new contribution of optimal transport is the first term, which is this gradient flow interpretation of these two objects, which gives a complete geometric way of looking into these well-known objects. Okay, and we'll see some examples of what we can get from this. All right, okay, so I'll stop here. So if you have any questions, let me ask. Otherwise, I'll see you next week, but don't forget to attend the lectures at the Fields Institute.
I have a question.
Yes, go ahead.
Can you remind me of the physical intuition behind the Fisher information, relative Fisher information, these sorts of in statistics, and also the score function?
They are
Like I
really
understand the definition.
concepts. There might be physical ones, but I'm not entirely sure of it. But they're really statistical concepts. So you understand what the log likelihood is, right? So the log likelihood ratio is trying to compare basically between two different densities. So that's your log likelihood ratio. The statistical interpretation that I know of Fisher information, it comes from something called a Kramer-Rao lower bound. You can look it up on Wikipedia. This basically tells you the amount of information that is contained inside data that is given by this Kramer-Rao lower bound. Mm, I don't know. All the physical interpretations that I know of this quantity comes from optimal transport. So I'll be going in some sense like a more circular way. So you should think of both of these Fisher information and this thing coming up as you're looking into heat flows. You're looking into all these molecules, they are diffusing in heat, and you're looking into the rate at which entropy is decreasing, and the gradient of this gradient and the size of the gradient is as I said, the score and Fisher information. That's basically the only physical interpretation I know. There might be others, but the statistical interpretations are much older. They come from this, as I said, this information bound. So look up Kramer-Rao lower bound. This is an important theorem to know.
Okay, thank you.
Can I ask a question?
Yes, please.
So for the when you define the subdifferential via the statistical or the optimization method, what if I want the
Right.
subdifferential at a different point other than the local minimizer?
Oh, okay. So you mean this one, right. So exactly. So then you can't do it. So this is very specific to the local minimizers. And as I'm saying, like the logic behind this is that you want to define the subdifferential at rho, and sometimes you cannot do it because things are not so nice at rho. So you define it as a local minimizer rho tau, and then you take tau going to zero, and you define that subdifferential at rho is whatever is the limit that you're getting from the subdifferentials of rho tau. Okay, that's the idea behind this. So you are not directly defining it at other points. You're only defining at a very specific sequence of nice points.
Okay. Is knowing it at those local minimizers usually enough for like the purposes of using this information?
Right. So you can actually prove that these local minimizers, I mean, you have to assume some kind of compactness to show that the local minimizers actually exist. But as long as you prove that for all small enough tau, the local minimizers exist, you can actually show that these local minimizers are very nice. In fact, they are very nice. They always have these gradients. The gradients satisfy these nice properties, and you're always converging. Whether whether the limit is uniquely defined at rho or not, that's a different question. But you always have a nice sequence. Again, you should think, the way that you should think of this is that, again, from here, this quantity which you are looking at here, this is not very far from your kernel, from your Gaussian kernel smoothing. In fact, if you look into something like this type, f of y e to the power minus 1 over 2 tau norm of y minus x norm square dy, and then you integrate this, and then you take this function instead of fx. Look into this function. What am I doing in this function? In this function, I'm really smoothing out the function by taking a tiny Gaussian ball around x, which has a standard deviation which is tau, which is square root of tau, right? And this is a very common way of smoothing. This and that, they are not very different. They are very similar. Instead of doing this integral, I'm doing a minimum. But otherwise, they're very similar. Does this kind of make sense?
Okay, thank you.
I should be doing an e to the power of fy, and then I take a log. Okay. So it's in convex analysis, this is a very common trick of smoothing, and that's where it comes from in optimization. But probabilistically, it's very similar to a Gaussian smoothing. So it's like log of the integral of e to the power fy times Gaussian. Okay. It just seems very strange when you see it for the first time.
I have a
Any other
question.
question? Yes, please.
Yeah, I have a question about the type signature of the first variation at the very beginning, because I thought it should take two functions.
In the first variation?
Yeah,
Why would it take?
because it's kind of like a gradient, right?
It's a
So I
directional
was,
derivative, but I have already have this. It's a you should think of it as a linear operator acting on these rho dots. So it's a directional derivative and rho dot, but remember what I've done here is that I'm saying that this object, this is like a linear operator acting on rho dot 0. And so every linear operator on this Hilbert space, I can write it as this kind of inner product. And so this term, this function is what I'm picking up, and I'm calling that's my variation.
okay. Right, because I guess I was thinking about just from calculus of variations.
Yeah, so
like,
yeah, exactly. From calculus of variation,
it-
it's the same thing. It's
but
even in the Euclidean case, this is the same thing.
yeah, I mean, but
Sorry, go ahead. Mhm. Are you still there?
yeah, I guess because it's usually, I think it's usually, or at least like on Wikipedia, if you go on, if you like look up first variation,
Mhm.
it takes two functions, right? It's like a linear operator. It's like a map that takes a function and returns a functional, right? So
Yes.
it basically takes two functions as input and outputs some
What are these
scalar.
two functions? So here it is taking u as one of the inputs, and it is returning this first variation del of u. What are the two functions?
Oh,
Right? It's the first variation of u. So u is already one of these things that you're already evaluating. Let's continue. Maybe let's ask this question again on Slack. I'll check the Wikipedia article and I'll tell you exactly.
okay. Okay. Thanks.
Okay. Anything else? Okay, if not, yeah, so please come to the workshop in Fields. It's going to be a great workshop, and I'll see you next week. Okay, bye-bye.
Thank you.